The human brain is sealed inside a pitch-black vault of bone. To experience reality, it relies entirely on scattered photons bouncing off external objects and physically crashing into your face. The front of the eye, the cornea, and the crystalline lens serves as a passive optical funnel, bending and focusing those incoming particles. The actual hardware that captures these photons is a paper-thin sheet of neural tissue located at the very back of the eye. This is the retina, the innermost light-sensitive layer of the globe. During embryonic development, the retina extrudes from the diencephalon in the brain. It is an exposed piece of your central nervous system pushed out to the surface. Vision is an active, energy-intensive data collection process executed by a biological transducer. If we zoom into the cellular level of this tissue, we find a massive, microscopic grid of glowing cylinders and sharp cones packed tightly together in the dark. These are photoreceptors. You have about 120 million of these specialized biological life sensors comprising this grid. The cylinders are rods. They are optimized for low-light detection, providing monochromatic vision in dim environments. The sharp structures are cones. They require high light conditions to provide color perception and sharp, high-acuity details. Cones achieve this by separating photons into short, medium, and long wavelengths, using distinct subtypes of receptor proteins called opsins. Operating a 120-megapixel organic sensor array results in the highest continuous energy demand of any tissue in the human body. This intense energy draw is driven by constant maintenance. Every day, 10% of the photoreceptor outer segments are physically shed and rebuilt to prevent the accumulation of light-induced damage. This incredibly dense, constantly renewing array creates an overwhelming analog feed of light data that must be physically translated into electrical spikes to be useful to the brain. This diagram shows a cross-section of a rod cell's outer segment. Inside, it contains a stack of membranous discs packed with thousands of dark, geometric protein structures. Zooming in, we find rhodopsin. It is a highly engineered, light-sensitive protein that acts at a binary switch. Tucked inside its pocket is a retinol molecule. In total darkness, this retinol molecule is physically bent, the 11-cis configuration, locking the switch in the off position. The trigger event occurs when a single photon slams directly into the molecule, violently transferring its kinetic energy. That kinetic impact forces the molecule to undergo photoisomerization. It violently snaps from its bent shape into a rigid, straight line called all-trans retinol. This microscopic mechanical shape change is the foundational mechanism of human vision, translating a physical particle into a structural state change. When the internal molecule straightens out, it forces the entire rhodopsin protein to stretch and alter its physical conformation. This diagram illustrates phototransduction, the chemical cascade initiated by that shape change. The altered rhodopsin binds to a G protein called transducin, forcing an alpha subunit to break away. The breakaway subunit activates an enzyme known as phosphodiesterase, which immediately begins destroying cyclic GMP molecules floating inside the cell. The sudden lack of cyclic GMP causes sodium ion channels on the cell wall to slam shut, blocking the inward flow of positive sodium ions. Cutting off that flow of positive ions causes the cell's internal voltage to plummet rapidly in a process called hyperpolarization. While most neurons fire when excited, photoreceptors signal the brain by doing the opposite. Their voltage drops and they stop releasing the neurotransmitter glutamate. The mechanical absorption of a photon results in a sudden halt of chemical release. That drop creates the electrical spike that constitutes 1 pixel of visual data. Zooming back out to the entire retinal array, millions of these individual electrical spikes generate a massive data feed every millisecond. 120 million individual photoreceptors are actively firing data at once. However, this system faces a severe architectural limitation. There is only a single output cable connecting the back of the eye to the brain. That cable is the optic nerve, a central tract of axons responsible for transmitting visual data to the visual cortex. This diagram highlights a critical hardware bottleneck. While there are 120 million input nodes, the optic nerve possesses exactly 1 million transmission lines. Transmitting raw, uncompressed video across a 120:1 bottleneck is mathematically impossible. The eye must run aggressive algorithmic compression on the 120 million pixels before the signal ever leaves the retina. This compression is executed by ganglion cells, a specialized layer of retinal neurons. Ganglion cells actively process the data by grouping thousands of individual photoreceptors into single units called receptive fields. Here we see the spatial encoding architecture they use: a circular receptive field divided into a central zone and an annular surround zone, all mapped to a single output line. The ganglion cell performs a calculation called decorrelation, mathematically subtracting the light value of the surround from the light value of the center. If light hits both center and surround equally, indicating a uniform image, the positive and negative signals cancel out to zero. The cell aggressively discards this redundant data, sending absolutely nothing to the brain. But if light hits only the center zone, indicating an edge or movement, the equation yields a strong positive integer, sending a large electrical spike down the output line. The retina acts as a highly efficient edge detection filter, transmitting only contrast and changes rather than a full picture. This heavily compressed data stream flows through a web of glowing wires that converge into a single, dense cable pulsing with information. Those 1 million output wires form the innermost layer resting on top of the retina. Looking at this diagram of the retinal layers, we see a counterintuitive layout known as the inverted retina. Incoming light must physically pass through the top layer of wires and ganglion cells before it can hit the photoreceptors at the bottom. This arrangement introduces a major architectural vulnerability. Those 1 million wires must eventually bundle together and exit the eyeball. To physically exit the eye, that thick cable of bundled wires has to turn inward and punch a hole straight through the photoreceptor sensor layer. The engineering required to solve the data bandwidth bottleneck created a permanent physical flaw in the biological sensor array. If we look directly at that physical interruption in the sensor array, we find a gap. This is the optic disc, commonly known as the blind spot. It is a 3 square millimeter area of the retina that entirely lacks photoreceptor cells. Every human possesses a literal hole in their visual field where absolutely zero photons are detected. To prevent you from seeing a dark circle in your vision, the brain runs continuous spatial hallucination algorithms, interpolating the surrounding context to seamlessly paint over the dead pixels in real time. Human sight is a highly compressed, aggressively filtered representation of the world, a mental construction derived from the brutal mechanical impact of photons crashing on a deeply flawed biological sensor.